linear phase can be realized. So I would say exact linear phase can be realized in digital systems. So whenever the application demands the linear phase, we have no option but to go for digital. Whether to choose analog or digital, if the application demands linear phase, we have no choice but to go for digital application or digital signal processing or discrete time signal systems. Yeah? I couldn't get linear phase means? Linear phase, I think we have done in lot about linear phase. Linear phase is the phase characteristics of anything is linear. So phi omega is a linear function of omega. We have magnitude and phase characteristics of any signal. If that is linear phase, if the system has a frequency response, hj omega, magnitude of hj omega is magnitude response, phase of hj omega is phase response. If this phase response is linear, that system is called as linear phase system. In analog domain, it's not possible to realize exact linear phase. Alright, we will see that when we actually have a look at discrete time systems. Next is there is concept called as multi-rate. Multi-rate is multiple sampling rate. Multiple sampling rate systems. This is possible only in digital domain, and there are so many. Now what are the disadvantages? Everything advantage comes with a disadvantage as well. So many, there is one more, applicability to low frequency range. Applicability to low frequency, very low frequency signals, something like a biomedical signals or seismogram, which are very, very low frequency signals. These can be processed by using discrete time systems easily. Now what is, before going to disadvantages, let us see what is discrete time system. We have analog system. Let's talk about analog system that is linear and time invariant, represented by h of t. Input is x of t, output is y of t. This is continuous time system. I want to make it discrete time. What am I supposed to do? Nature is continuous time. It means I have a big block. Here the input is x of t, output has to be y of t. It means this continuous time analog system is to be replaced by an equivalent discrete time system to make use of the advantages of digital technology for processing of analog signals. So this block diagram is going to be acting as equivalent of analog system for processing of analog signal. Equivalent discrete time system, how to make use of discrete time concept in processing of analog signals is what is this equivalence. Alright. So first block xt must be converted to its discrete time, and this is being done on the basis of a phenomenon called as sampling theorem. What is the sampling theorem? So I must have what is known as sampler or sample and hold circuitry, S and H. It's also termed as SH. Why sampling? Why hold? We'll see little later. Now xt becomes x of nt. Now x of nt, I have samples. Now the sample values can take up any value. Say for example, xt goes from minus 5 volts to plus 5 volt. I am only discretizing the time axis. I am not doing anything with the y axis. The magnitude axis I am not doing anything with. Alright, so that can take up any value from minus 5 volts to plus 5 volts. What is that minus 5 to plus 5 volt? It is uncountably infinite values of the y axis of x of t. Signal x of t can take up any value between minus 5 to plus 5. It can take up any value of t also. That is x of t. Now when I take x of t to x of nt by using sampling, what am I doing? I am discretizing the x axis. So countably infinite set of t values now are becoming countably infinite. Uncountably infinite set is converted to a countably infinite set. That is the meaning of converting t to nt. But remember, the y axis remains the same, which is uncountably infinite. I can take up uncountably infinite values from minus 5 to plus 5 volts. Now if I discretize this also, what I need to do? I must convert these values of x of nt by using analog to digital converter. So what happens in analog to digital converter? Suppose it is an 8-bit ADC. So any uncountably infinite values from minus 5 to plus 5 will be converted to how many infinite values? By an 8-bit ADC, 2 to the power 8. 2 to the power 8 is 256 values. There can be countably infinite values, but out of anything out of these 256, 0 to 256, these are countable values. Understand? So ADC converts, ADC quantizes the magnitude as well. ADC discretizes the magnitude as well. Now what is the output of an ADC? Output of ADC is sequence of numbers. This sequence of numbers is processed by a processor. This is called a digital processor, a digital signal processor. Now digital signal processor has an algorithm, something like a filtering. A filtering algorithm is presented and the sequence of numbers is processed. I want to convert that back to analog. So I must make use of a DAC. What is DAC doing? DAC is converting the digital values into corresponding analog values. Followed by that, what is required is a low pass filter to remove the high frequency noise contained in the output of DAC. Now let us see the waveform at each of the places. Any question in this diagram? So what is this block diagram? This is a block diagram of use of DSP to process analog signal. These two are equivalent. Now if suppose, what is x of t? I would say x of t is something like this. X of t. This is x of t versus t. So the signal available here is x of t. What is the signal available here? Now this is sampled. Sampled means you have only sampled values. These arrows are drawn with green line, green color. This device is not, this seems to be color blind. So please see that these are green lines, alright, arrows. So samples of x of t. So these green lines are x of n times capital T. What is this x of n t? It is x of t sampled at t is equal to n times t. This t is called as sampling interval. This T is called as sampling interval. What is it? It is the distance between these two lines, capital T. So X of NT is there. Now what is the output X of output of ADC? Output of ADC will be like here it is, these are sampled. If I sample these as well, so 0 to 5 volts, uncountably infinite set. Now I am making it finite. So I have countable values 0 to 256, 2 to the power 8, 8-bit ADC. Alright. So these are, so this value could be 2.96 volts analog, but when it comes to digital, it may be 2.9 quantized value, because 2.9 could be possible, one of the possible values out of those 256 values when we have used quantization for 0 to 5 volts. So each step is how much? 5 divided by 256. 0 volts is 0 volts. Next voltage available for measurement is 5 divided by 256. Next is 10 divided by 256. So 5 divided by 256 is the least count of the voltage level in the ADC. You understand? So then I will have finite values of the magnitude. So now I have both. So here I have what is known as sequence of numbers. So there is the time sense is lost. Time sense is lost here. It may be present, it may not be present. I may have just sequence of numbers. So friends, the digital signal, so this is called as digital signal. What is digital signal? It is sequence of numbers. What is discrete time signal? Discrete time signal is not sequence of number. Discrete time signal is only time is discretized. Although there is a distinction between discrete time and digital, we are not going to differentiate it. Alright? We are not going to differentiate it. X of NT and X of NT bar, quantized X of NT, is going to be same as discrete time or digital. Now what is the output of DAC? Output of DAC will be something like this. If suppose that these green lines are the output of ADC, assuming that, let me draw it again here, something like this. If this is the output of the digital processor, now output of DAC will be what? This is fed 0. 0 is, it will come here 0. Then this value will remain for this time. This value will remain for this time. This value will remain for this time. Then it comes here. Then it comes here, and so on. So output of DAC will be a staircase kind of a waveform, digital to analog. And then this signal will have, what are these? These are high frequency noise. These lines. These discontinuities equivalent to high frequency noise, which can be reduced, which can be removed by applying it through, by passing it through what is known as low pass filter. And the output of the low pass filter is, and so on. This color is output of low pass filter, which is actually called as Y of t. So X of t is a smooth signal, Yt is a smooth signal. But to obtain this, instead of one single analog circuitry, I have made use of entire thing. This is so disadvantage could be increase in complexity. Complexity increases in digital signal processing. So complexity means cost also increases. But this can be, the cost disadvantage can be removed by making use of this digital processor in time sharing mode. Time sharing of processors. Processors can be shared because processor is high frequency processor. It cannot be used for processing low frequency data. If at all it has to be used, I can make use of this processor in a time sharing mode. Example could be digital computer of today Say for example, in an intensive care unit, there are about 32 beds or 64 beds or 100 beds, but only one doctor attending to all the patients during night time. How is that happening? There is only one processor, one CPU in front of the doctor, who is only observing all the time, and whenever there is an emergency, attending to those patients. So one CPU is being time shared between those many patients. Each patient will have about 3 to 4 embedded systems monitoring the patient's health. All right. Some device is monitoring the heartbeat. Some other device could be monitoring the blood pressure, sugar, and all these embedded systems are controlled by a single processor. So 5 to 6 such embedded systems controlling health of one patient, 32 such or 64 such patients, 100 such patients. All the embedded systems are connected to a one single CPU. And then what is doctor doing? Doctor has windows in front of him. A large screen with so many windows. Each window is occupying health of one doctor, one patient. This is time sharing of processor. One PC being used for hundreds of the patients. What is the time sharing? Like this, time sharing processor can be done in several applications. All right. So by that, what is happening? By that, the same PC is being used hundreds. Instead of using 100 PCs, I am using one PC for monitoring. So have I reduced the cost? Yes. So complexity increases the cost. However, if I make use of time sharing, then the cost can be reduced. The second disadvantage. Any questions so far? The saturation of digital technology. The saturation of digital technology, once again, I have to take you to Moore's law. Moore's law is saturated. How long will this survive? This question was asked in the scientific community for the last 50 years and will be asked for next 50 years. What is the effect of reducing the size of the transistor? Today it is something like 22 nanometer or 18 nanometer. After 18 months it will be half of it, 9 nanometer. After once again 18 months it would be 4.5 nanometer and so on. How long will this continue? Was the question posed and the answer was given. Now why this is being saturated? Why do we call this as saturated? Moore's law is saturating. It's because of the fact that transistor length or transistor size, how much it can be. What is the size of silicon atom? Whatever we are doing, number of transistors getting fabricated on a single chip will have several disadvantages. When you increase the number of transistors, when you reduce the size of the transistors, there are many other effects which you must be learning in the course of microelectronics. Now those effects will also be there in the functioning of an integrated circuit. But can it go below the size of the silicon atom? Can there be a transistor, one transistor per silicon atom or two transistors per silicon atom? Possibility, I don't know. So what is the size of the silicon atom? 1 angstrom. 1 angstrom is how much? 1 into 10 raised to minus 8. Minus 10 meters. 1 into 10 raised to minus 10 meter. It means 0.1 nanometers. Alright, so up to that point we assume that the Moore's law may last for. Beyond that what? So there is a limit to Moore's law. And friends, what has been achieved by the computational power, with the digital computational power, it was said that a single human eye, whatever processing it does, cannot be done by entire computing power available on the earth. So that's the limit of saturation. If you want to have an artificial eye to be developed, it cannot be developed with entire computation power available on the earth. If that is the situation, then to have an artificial eye, you would require entire computational power. And the size of the eye is so small. So probably that could be a limitation of digital technology. That's why people are now thinking of combining analog and digital. So once again, the technology is being moved from digital back to analog. With whatever are the advantages of digital technology, wherever it can be used, you use it. But wherever it's not possible to use it, go for analog solution or go for what is known as a mixed simulation, mixed solution, analog and digital together. Analog and digital on a same integrated circuit. Is that possible? The answer is yes. Analog and digital on a same chip, which is called mixed signal circuits. Alright, so that is possible. That's why people are going back to analog, where we find disadvantage of digital technology. Alright.